We begin our demo by introducing the Fresco plant, a facility equipped with a basic automation. It uses OPC UA compatible controllers to collect real-time data and maintains asset documentation in a wiki. However, there is no conceptualization or unified namespace in place. That means that data exists, but it is fragmented. Devices, areas, and metrics aren't consistently named or linked. As a result, automation integration and AI-driven insights are limited because systems can reliably interpret or relate the data across sources. We kick off data contextualization with the asset hierarchy extractor, an on-prem AI agent that reads unstructured wiki content and builds a structured view of the plant, identifying areas, devices, and resolving duplicates or inconsistent naming across articles. In parallel, it maps device metrics by analyzing the OPC UA model, linking semantic knowledge with the live data sources. The agent runs an YAMA 3.8b model locally, ensuring full data privacy. It then sends two MQTT messages, one for the UNS configurator, which applies the hierarchy via Node-RED, generates flow, and starts streaming live data device into the Sparkplug B format. The other to the rack importer containing only cleaned up hierarchy from the wiki. It updates a vector knowledge base for the future LLM use. Now that the structured data is available in Sparkplug B format via unified namespace, it becomes usable across the enterprise. To enable this, we have built an historization module that listens for the device registration messages in MQTT. When a device registers, the module dynamically generates snowflake tables tailored to this device, including its specific metrics. It also listens to the real-time data published by the Node-RED every second and stores this in a raw format. This raw data feeds into the dynamically built tables, creating structured views that can be queried and used for analytics reporting or AI-based reasoning. Now we enter the second part of the story, how we use the contextualized data we have built. We have developed a chat-based interface powered by the Open Web UI, connected to the multiple LLMs via Grok API. At the core of the experience is YAMA Versatile model, a model perfectly suited for handling technical queries with a precision and contextual understanding, and it runs with exceptional performance thanks to the Grok low latency backend. The assistant isn't just conversational, it understands the plant layout through the vector database built from our asset hierarchy and supports rich practical interactions. The first use case is simple but powerful. User can ask about the plant layout, explore areas, devices and their metrics, or inquire about the purpose of the specific equipment, all through the natural language. But we didn't stop here. We have integrated the custom MCP tools into the chatbot, enabling it to communicate with the historian database and UNS that lets the user to retrieve the latest values for any device or metric, query trends or current status for from Snowflake, and even write the new set points back to the devices via Sparkplug B over MQTT. These interactions are context-aware. The system knows which area or device is being referenced, even if the question is vague. The result is smart, safe, and interactive assistant that turns chat into the control interface. But we didn't stop there. Instead of just solving today's problem, we asked, how will manufacturing and process automation work in the future? To explore that, we built a business rule framework, a system that allows users to define business logic in natural language, which is then transformed into the Python code using the same LLM based on compound beta model and MCP tools already used by the chatbot. Here how it works. The user asks for a business rule, for example, if the air conditioners in a cooling area are out of sync, set them to the minimum value among them. The chatbots call special agents that consult the runtime, which expose API to retrieve all currently active business rules and available MCP tools from registered MCP servers. It checks for duplicate or overlapping rules. If the rule is new, it generates a Python code embedding the required tool calls just like it would be in a normal chat interaction. The user reviews and approves the generated rule. Once confirmed, the rule is saved and executed automatically by the business rule executor, which runs all the active rules once per minute. The system brings us closer to the self-adaptive intelligence control layer where operators and engineers collaborate with AI to manage automation safely, efficiently, and in real time. Of course, the entire solution was smoothly and easy deployed on the Vultr infrastructure. Huge thanks to the organizer, Vultr, Grok, and Snowflake for the opportunity. For more details, please check out on GitHub.